Não.
Então para que é isto?
Agora o som da Mariela.
Ah, está bem. Não queres? Olha, havia de experimentar o som. Olha, mas não se querem.
Agora tenta mudar. Ele já está no limite de recorte online. Já está no limite de recorte online.
Como é que quando é que vocês conseguem ver se o som já está a chegar lá fora?
Good morning. So today we will continue the third session of Friday at ISISE, and today we have Mariela that will present the work of her PhD thesis titled Innovative Solutions for Connections in Modular Tubular Structures for Wind Energy Systems. The presentation, as you know, it will be more or less 20 minutes. After we have a discussion that will be made by a colleague, and after we have the public discussion, and at the end we take more or less 1 hour.
Okay, hello everyone. Well, I think we all know each other, but in any case, I am Mariela. And I would like to explain a little bit today about what I am doing for my PhD. I have to say that I am in the earliest stages, so you will see a lot of things of what we want to do instead of what has been done until now. And I'm carrying this research under the supervision of Professor Carlos Rebelo, Traiano Tancova, and Professor Ricardo Branco from the Department of Mechanical Engineering. So I will try to introduce the topic a little bit, where this research came from and justify the validity of it, then to explain the objective that we have, the methodology that we try to use, and then conclude with some final remarks. So to introduce the topic, I wanted to show this image. I don't know if with the light you can see well, but here you can see the standard size of the current wind turbines, or what we had, let's say, like 5, 10 years ago. And now you see what the market is producing. So this here, well, it's the Eiffel Tower, if you can see. So just to have an idea, this is probably like 5 megawatts capacity, and these other ones are between 14 and 16. The nacelle, which is the housing in which we have all the electrical and mechanical equipment of one of these towers, could weight 500 tons. So as you can imagine, we need very big and very heavy and very strong supporting structures to have this type of wind turbines. But actually that comes with a lot of difficulties from a logistic point of view. For example, in here I have, in the case of an onshore wind turbine, the comparison between the ideal diameter of one of these towers and what we can actually transport by land. But this is not only a problem of onshore wind turbines, because actually offshore we only have in the world more or less like 25-30 vessels that can transport this type of wind turbines. And yeah, I'm talking about the whole world. So what is happening is that many countries are switching to smaller turbines again, because it's so difficult for them to find the equipment to make these installations. So in summary, we now have very big turbines, larger turbines, that require bigger and heavier supporting structures. And this comes with 2 new challenges, some of them from the technical feasibility, because we now require a very high level of precision, and this has made the manufacturing costs very high as well. And some other challenges from the logistics point of view, because they are very difficult to transport, they are very difficult to install, and sometimes they can make potential wind sites unfeasible just because it's impossible to reach them. So right now, the industry is trying to work on how to reduce the cost, on improve the technologies that are being used, and also all of this to facilitate the installation of new wind farms. And as I told you before, what has been happening is that we are using nowadays smaller wind turbines, or even for the big ones, there's a rise in the popularity of modular and light structures like jackets or lattice structures or things made out of panels, either concrete, steel, you name it. So in our case, what happened was that we started working in partnership with a company called Wonder Ocean that has the offices in Figueira da Foz, and they came up with this idea to have a modular tower that is self-assembled. So basically you have some concrete and steel panels, you have a steel skeleton structure and then an outer concrete shell to protect the tower from the elements, and there's an internal rail that allows for a small crane to grow with the tower and start assembling all the pieces. So we started developing this project, but then we came with a challenge, let's say, that we have a lot of connections. So because of the modularity, because of the panels, yeah, they are easy to transport. They don't have any limitations in terms of size, because now you can do them exactly in the way that can fit a lorry, let's say. But we have an enormous amount of connections. So that's how everything began. How do we do this? How do we solve these connections? We looked at what has been done recently, especially for tubular elements, because the reticular steel structure is made out of tubulars. And we saw a lot of, let's say, welding, bolting. Then we found for other structures, some plug-like devices and inserts, but this has never been applied to such large structures. And then we saw the potential of additive manufactured joints, and very conveniently, we have now the facilities here in our lab, and some other solutions like casted joints or composite wraps. So having this in mind, basically our problem is that we have a lot of modular structures now for wind energy converters that require a large number of connections that must be of high quality, easy to install and uninstall, and provide sufficient fatigue and ultimately limit the strength and resistance. So we want to develop an adequate set of connections for tubular sections using steel or composite supporting structures for wind energy converters that can be either offshore or onshore, like modular or jacket structures. And how do we want to do this? So, as I said, we looked at what has been done recently, and additive manufacturing seemed like a very feasible idea. And we have now the facilities here in the lab to produce joints or pieces or whatever with additive manufacturing. But that will help us a lot with technology improvement. And I have to say that additive manufacturing is already used in the wind sector. So it's like we got the inspiration, but for example, you already see welding in monopiles, just internal welding for maintenance, for repairs, for operation. And it's also highly implemented in the production of the blades. But if we really want to take advantage of additive manufacturing, then we must do structural optimization that will allow us to reduce the cost, because then we know that whatever we are producing is actually going to be the most effective shape. And now I will try to explain this a little bit more in detail. So we begin with developing a concept that later goes to a topology optimization and then to a finite element analysis. So this first row is like just to have the main idea. It's like the first iteration. But it's iterative because we can have many different concepts, we can have many different topologies optimization, we can vary the parameters however we want, and each time we will get something different, and we have to evaluate if it's reasonable, if it's not, if it serves our purpose. So this is a lot of the work until now has been focused on this part. Then we go into a lifetime estimation, durability shape, re-engineering, production testing, and validation, but I will go through each one of them. So regarding the first stage, so as I told you, we develop a concept, then we do a topology optimization in which we only use static loads and also only linear elastic material parameters. So we only input in this optimization the Young's modulus, Poisson's ratio, and the density. And we use as objective function the strain energy and as constraint the volume. So this is just like a first step, just to have an idea. From that, we get a first shape. But that shape, because we are only introducing the Young's modulus. If you see the algorithm of the shape optimization, it only focuses on the Young's modulus. We know that we have a very stiff shape, but we don't know actually its resistance. So after that, we go to the finite element analysis, in which we include the plastic material properties. And we can do this as many times as you want. You can change the number. When you are developing the concept, for example, you can change the number of bolts, you can change the diameter, you can change the outer tubular, you can change all the optimization parameters, anything. So at the end, when we are satisfied with this, then what we want is the surface node stresses to go to the next step. So this, as I told you, is what I have been focusing lately. So we develop a concept that it's just putting an insert inside two tubulars and putting everything together by bolts. Then we go to the topology optimization. We get a first shape that we know that it's very stiff, but we don't know its resistance. So then we go to the finite element analysis, and then we get a lot of data for the surface nodes. And this can go as many times as you want. So after that, we go to the lifetime estimation and reveal shape. So after we get the surface node stresses, we can go to the lifetime estimation. Now in here, it's where we are going to input the stress history of the wind tower. So now we are not only talking about static loads, but we are going to have actually the history, the cyclic history of the loads of the wind tower. And in here, we also need the fatigue parameters to do this modeling. After that, we will get the surface nodes life prediction, and we can do a durability shape optimization that is based on this life prediction. So in here, the objective function is to minimize the maximum damage and to control the volume. But again, yeah, we will use here again the static loads. And then we get like a second optimized shape. Right now, what we are doing is trying to find out this. So we are focused right now on finding the cyclic properties of the material. How are we going to do that? Well, through an experimental campaign. We have divided the experimental campaign in two parts. The first one is focused on low cycle fatigue and fatigue crack growth, and the second part in high cycle fatigue and fatigue crack initiation. So in the first part, we already started, let's say, so we have the shape of the coupons that we want to test, and the program has been detailed, and we also made the first test in the lab to see how we can print this wall, which is going to be basically just like a big wall, like a big plate, and we are going to get 3 fatigue specimens through the thickness of that plate to also evaluate if there is some kind of variation of the material properties along the thickness of the printed material. After we do that, then we go to the re-engineering and production, testing and validation. So we get our final shape that now we know that makes sense, that has sufficient strength, and also that it has the desired lifetime. So that's like, let's say, this comes from process of iterations, but let's say that's like our ideal shape. And then we have to do the re-engineering, which is very important because not everything that we do in a computer can actually be produced by the capabilities of the machines that we have in the lab. So even if you have the most perfect ideal shape, you still have to compare that to what you can do in the lab. So maybe there's something that is too thin, or there's an angle that is too close. So all of those things have also to come into consideration. In this part, I want to highlight the work of our 2 colleagues, Carlos Hu and Kaique Monteiro, because they are working very, very hard to find out what can we print, what are the capabilities of the robot, and trying to build some kind of like database so we don't have to go through a calibration process every time that we want to print something. So after that, we get our last and final shape that we have to check again for life estimation because maybe we altered some details that were important for fatigue. And then to production, testing, and validation. And then in theory, that's done. But to conclude, as conclusion, let's say, yeah, I think it's very important to highlight the importance of modularization and simplification in the wind industry. As we saw, it's quite important to make this kind of new emerging renewable energy technologies available for everyone. Also, I think it's important to highlight the importance of using new technologies like optimization and additive manufacturing in joint. I want to highlight also that, for example, this process or this type of optimization, you can find it in some literature in different ways, similar, but it has always been applied to mechanical parts. So we got some information from what they do for pieces of engines or mainly engines. But it has never been applied as such in a structure. To know if the shapes that we are coming up make sense, let's say, we are also comparing with some traditional types of joints, so maybe only using bolts or using some plates and shear or some other devices that are available in the market. And we found out that our shapes are usually more efficient, like in terms of strength and volume, in over 60% of the compared cases. And also that this has a wide range of applicability, because I am talking about wind towers, but if we have a detailed process on how to optimize a piece, taking into account not only the material that is being used, but its strength and its fatigue life, then we can expand this to a lot of things. I don't know, bridges, walkways, stadiums, anything. And then the next steps were, first of all, is to complete the experimental campaign, the first part, that is the low cycle fatigue and the fatigue crack growth, to define the stress history of our tower that we are using as a case study, the one that I showed you with the Wonder Ocean, to calculate the lifetime of our piece, and to do the durability shape optimization. So, an acknowledgement to the funding of this work, which was initially the project of the self-erecting tower, and now the research grant by FCT. And as a trait for today, let's say, I brought some samples of what has been done in the lab. So you can take a look, because I think many of you have seen by far, like the things over there, but I don't know if you have had the possibility to actually touch them or see them, or or just to take a look at what's the final finishing, what are we talking about. These two, for example, one is produced by Wired Arc Additive Manufacture, that is the big robot on the right, if you have seen it, and this one is by laser. So you can also compare the finishes of these two blocks. This is the one that we produced to test the plate that I have to do for the fatigue experiment. So if you just want to basically touch and have like a closer feeling of what we are doing in the lab, and Carlos and Kaique know these pieces very, very well, probably by memory. So I hope you enjoyed the presentation and got to know a little bit of what I have been doing lately, and let's say what the additive manufacturing group is doing. Thank you so much for your attention.
Thank you, Mariela. Appreciate your work. I think so very clear. Well, thank you. Thank you. So now is Luis.
My turn is. Well, first, congratulations. Well, very well presented. Very cute presentation as well.
Thank you.
Well, now the hard part where I start some questions. Well, I got some doubts about how will you integrate this new technology in the tower, like everything, just connections? How are you going to do the combination of those?
Mm-hmm. So far, we are only thinking about the connections. So the idea is that you have this device, and then you have the reticular steel structure that is going to be a tubular. So you put the device, you bolt it. Obviously, the device has some kind of stopper, so it doesn't go inside the tubular. And then you come and you insert the other one. And also because, the life of wind farms is quite short. So you need to have something that you can put and then take out in probably not that long very period, not very long period of time.
Okay. Regarding that, not that I know that you are focusing on the connection, so I guess one of the questions that I have is when you talked about parametric stuff, parameterization after the iterative process, etc. What are the limits for that parametric stuff? Because in the beginning you talked about the size of the towers. Are you focusing on the newer ones or on the going back to the more modest ones?
Yeah, well, right now, let's say like the height of the tower, of this tower that we are using as a case study, is 160. meters tall. And yeah, it's quite big, let's say. But the size of, we have tried to do the optimization. One of the variables has been the size of the tubular. Because the idea behind this tower is that with these modular panels, then you can adjust to whatever height and to whatever diameter you need. So we have tried different outer tubulars depending on different towers, but the main one is supposed to be 160. After that, we made some tests to see how this shape would change with the geometric constriction of the outer tubular. But the main things that we have worked in parameterizing, let's say, or the main parametric values that we have explored are more related so far to the optimization algorithm. Because to the connection, and then in the connection, when you do the optimization, you can choose a lot of algorithms, you can choose different material models, you can choose different objective functions, constraints, restrictions. So that's what we have been exploring deeply.
It's quite new.
So,
Okay, so one, I think it might be the last bit, I'm not sure. The great question, money. How does the system, the new technology justify that? Probably the.
Yeah, that's actually a very, very good question. So to assess this point, what we want to do at the end, well, now when we are going to print the plate, the idea is to measure the energy consumption, the material consumption, and all the consumables that we have in the process to be able to compare. But another thing that we want to do is at the end, when we came up with the optimized shape, we would like to produce it, let's say, by casting and then by additive manufacturing. So we can compare directly what is the difference between having an optimization and using a conventional production process and then using additive manufacturing. And we have to think that it's, yes, right now it's probably more expensive. I won't say it is because I don't have the data in my hand. Probably it is more expensive. But I think the importance is that this opens a possibility to do things that before we couldn't. So with time, probably we'll get a little bit more economic, and also we can achieve things that with conventional fabrication methods are also not possible. Because, for example, in terms of fatigue, we can do shapes that are ideal for fatigue. So instead of having like very sharp notches or having like abrupt changes in the geometry, we can smooth everything and actually produce it that way with additive manufacturing.
That will bring another problem, the material properties within itself, because it might not guarantee the flow. It's stressful that you want, etc.
Yeah, that's it.
Yeah, I'm not sure if I have anything else, to be honest. You explained pretty well, especially at the stage that you're at. So I guess I'm finished with my questions.
More questions for the colleagues? Presentation.
If we have time. Thank you, Mariela, for your presentation. Also, I get here late. Just I could see the last slide and the material, the connection that you used. Maybe my question just will be about the material that I saw. This material that maybe you will model in the software.
Yes.
Which type of material do you use? Normal steel or?
So one of the cubes over there, it's normal steel, but we already have some experiments that were performed last year, and we have the material properties of this steel.
Okay. And the thing is, it wasn't every time I question about this type of constructions, robots or 3D printing. Imagine a normal connection, it has a smooth face. But this type of connection, it is not completely smooth and stress concentration and makes probably some cracks.
Yes.
And do you have any idea to apply those limitations? Because I guess it is something, maybe some problem happened. Definitely for wind tower, it has quite a lot of vibration probably, and this damage concentration probably makes some cracks or initial cracks that makes problems.
Yes, you are completely right. So one of the biggest, let's say, concerns right now about using additive manufacturing is because of the surface finish. Because then it's very prone to fatigue, to start to have cracks. The thing is, well, what has been researched until now shows that even though the cracks may initiate at an early stage, it's very difficult for the cracks to propagate because the material inside is like so irregular that the crack has to go like into a very sinuous and difficult path to actually propagate. So it has been determined until now that crack initiation might be earlier than in conventional steel, but crack propagation takes a lot more time. But that's why we want to do our experimental campaign. And in the second part, in which we are going to assess high cycle fatigue and crack initiation, we want actually to do exactly what you said, so to identify where do we have some stress concentrations in our final shape, and then make like a small sample of only that part and do the crack initiation experiments. So we can find out how is it going to be in a sample of our full joint.
More questions? I have a question. It's about the experimental campaign that you are preparing. Could you explain a little bit more about what you intend to do and when?
Yes.
I think that will take some time for all the campaign. So could you clarify?
Yes. So well, when it's I don't know when. As soon as we get more gas in the lab, we can produce the wall that then will be sent to LIP, to make the cutting of the specimens, and then this will go to the Department of Mechanical Engineering to do the testing. What we want to obtain from this first stage of the experimental campaign is basically the SNN curve. So that's the main goal of our first experimental campaign, because after that, then we can easily go to make a material model and use it for the lifetime estimation.
Any other question? So I think we finalize here this third session. Thank you very much. Thank you very much, Marielle, for considering the time. Really.
Thank you. Okay.
And we meet again here